Okay, so this is lecture 6. This is the third lecture on causal structure learning, and this is going to be kind of about causal structure learning from interventional data, and not just in kind of the passive or batch setting where somebody hands you a data set of interventional data, and then you go off and like run a causal structure learning algorithm on it, but also in this kind of active setting where you get to choose either ahead of time or kind of sequentially which of the interventions that you want to do. And a few, I guess, administrative notes. I'll be returning PSET 2 at the end of class today. And then PSET 3, I posted it a little bit late, so that was posted on Sunday if you haven't seen it yet. And that'll just be due. I'm not sure what the latest I can take it is, but let's say Friday, 11:59 p.m. You can just send that to me by email. And it's not on the board, but we are going to be having the study session again tomorrow in the same room, 24307. If you haven't already been there, that information is on the syllabus on the course website. So you should be able to find that. Yeah, so any questions before we get started? Cool. So today, yeah, we're going to be talking about identifiability from interventions. Kind of an underlying assumption I'm always going to have throughout is that we're always seeing observational data. So we kind of start with like, okay, at least we've observed this system in the setting where we haven't intervened on it. And I'm going to try to remember to be explicit about that when I'm writing out the like theorems and stuff. But I'm going to be denoting that by this I empty set. So that's going to be kind of this empty intervention or this observational setting. And if you remember the way that we define interventions, they had these two components to them. They had the intervention targets, which were x of I, like this. And we'll have, this is just xi of the empty set, is the empty set. We're not intervening on any nodes. So we don't have to specify the other part, which causal mechanisms we replace for those nodes. So yeah, last time, I guess we kind of established in lecture 4 that if we just have this type of data, we only have observational data, then all we can get is Markov equivalence. And similar to kind of the way that we use these like intervention augmented graphs to extend our identifiability or reasoning about identifiability of causal quantities in the policy evaluation section, we can kind of use that as a tool to be thinking about what we can identify from interventional data. In the case of those policy evaluation questions, we're mostly considering just like a single intervention. So all we have to do is introduce like one extra intervention node. So real quick, I'm gonna define a little bit more loosely than I did for the single node intervention case, basically this extension to when we have multiple interventions, because we're gonna have to keep track basically not just of an observational distribution and an interventional distribution all at once, but like an observational distribution and a set of interventional distributions. So it's going to be our first definition. And we're going to say, we're going to denote the set of interventions as this calgraphic I, and that's going to have this I empty set along with I1 through IK. So let that be a set of interventions. So we'll define the interventional causal graph. Similar to how we denoted it with a superscript, just one of these normal i's, we'll have superscript calgraphic I. And I'm not putting here, but obviously there's some graph G that we're augmenting with these interventions. And we're going to do everything in the setting of DAGs today. So just put that here, let's say G is a DAG. Okay, so this interventional causal graph is going to be a graph with nodes X, calligraphic I, which is our original set of nodes, along with this set Z of intervention indicators, one for each intervention. And then the kind of funky thing with this definition is that these intervention indicators, kind of only one of them can be active at a time, because data can only be coming from one intervention. Like, even if we did have, say, some intervention like I1, I2, and I3, and I3 was like a combination of I1 and I2, we would still be including this as an extra node. So we'd have zeta 1, zeta 2, and zeta 3. So we have to have kind of this switch that says which of these intervention indicators is supposed to be 1. So that's going to be this zeta star. And I guess this is not a set, so we have to put it there to make this proper. And then it's going to have as edges, of course, the edges that we had in the original graph. So this is for any pair of the original variables that were actually connected in the original graph. Sometimes I'll refer to these as the system variables to distinguish them from these kind of intervention indicators that we added on. And then it's going to have, so that's the first type of edge. It will have an edge from each of the intervention nodes to its targets. And then it will have this final set of edges from this kind of like master intervention indicator to each of those kind of binary intervention indicators. So this node zeta star is going to take values in, I guess, 0, 1, up to k. And basically, you know, we would do the same thing with the structural causal model that we want to define via this graph by saying that if we have an SEM M with causal mechanisms I for each of those variables, each of the system variables. Then we can define a new interventional structural causal model, and similar to this kind of arbitrary choice that we had to put on the intervention indicator, we are going to have to put like some arbitrary choice of distribution on this guy. But then the rest of it is not arbitrary, so we can have each of these intervention indicators just takes on the value 1 if the kind of main one takes on this value k. So that's what's encoding that only one of these can be one at a time, and if this zeta star is equal to 0, then all of the interventions are kind of turned off. And then the way that we combine the like interventional mechanisms say that the interventional mechanisms for IK are denoted by GXI superscript K. So we'll get one of these for each of the intervention targets. Then what we want to do is kind of this similar, using the indicator to say our variable xi is going to take on if all of the parents, so its parents are just the intervention nodes which have that as an intervention target, right? So if, let's call those, I think I called them I of xi, right? So this is the set of interventions that have xi as a target. So if all of the intervention nodes associated with an intervention on xi are equal to 0, so I guess really I should be writing zeta k, this is the Kronecker of zeta k equals 0. Say for all, this is like a little bit of abusive notation, just the indices of those interventions. So for all k in that set I of xi. So if all of those are 0, yeah, I use the original causal mechanism, the observational one. And otherwise, I will use one of the interventional ones. So this would be 1 if that zeta k equals 1, and then times this g xi k. And here I'm just writing the functions as kind of dropping the arguments. So really this is a function of the other system variables and that exogenous noise term, and this is a function of the other variables and the exogenous noise term. So this is put a little bit more formally in the notes, which are already posted on GitHub. Is that clear? This is all just a little bit of sleight of hand to put all these interventions into a form that we already mostly know how to reason about. So, for example, if we were to have a intervention on this graph, and we did, say, one intervention I1 that had as its target just this x2 node, and then another intervention that had as its target both x2 and x4, then this would basically be our graph, and then we would have this zeta star that points to both of these. Sometimes I'll just drop the zeta star because it's always implied. Like with the intervention variables, I actually have to tell you what their targets are, what their children are. With this one, its children are always these other intervention variables associated to each of the k interventions. Okay. Right, and the point of doing it this way is that we basically get back to being able to write down distribution so that we can think of our interventions as conditioning on these intervention variables. So we have this full distribution over the x's and these zeta variables. So if we have, if we're conditioning on one of these variables being equal to 0, that is going to be equal to the interventional distribution of this. Okay. So now we'll kind of transport all of our notions that we had for identifiability from just observational data onto interventional data. So in particular, we can define Markov equivalence, an interventional version of it, which we'll call I-Markov equivalence. So again, we'll have this set of interventions, calligraphic I, such that there's observational data in there. Then we're going to say two DAGs, G and G prime, are I-Markov equivalent, or interventionally Markov equivalent. If their interventional graphs now have the same set of d-separations. So this is why I had this independence symbol down here, so that this is referring to the thing that gives you the set of d-separations, and then this calligraphic I is the one that is the set of interventions. So we want them to be equal, and then we'll call them I-Markov equivalent. Okay, so by extension of our previous results, we know that two graphs, G and G prime, are I-Markov equivalent if and only if these two graphs, their interventional causal graphs, have the same skeleton and the same unshielded colliders. So the kind of new thing that we have is that the intervention nodes that we introduced can form some new unshielded colliders and kind of give us additional orientations on top of what we already had. I will just write the term on the board. It has like the same definition as we had in the case of observational data. So the I essential graph is that graph where we kind of take all of the things that are Markov or interventionally Markov equivalent. So that set, I think we'll be using some. That's going to be denoted, all the notations the same. We're just putting I somewhere with everything. The interventional Markov equivalence class, you can basically, in some sense, take the union of all of those directed graphs to get the I essential graph. And what the union does, right, is like gives you, if you always have the same directed edge in all of the graphs, then we'll spit out that same edge in the I essential graph will also be directed. But if we have it conflicting in two graphs, then in the I essential graph, it'll be undirected. Okay. So hopefully this is a bit of a review of these terms about Markov equivalence and the equivalence class and the essential graph. Now we're just throwing I onto everything. So the first result kind of reinterprets this characterization that we developed for Markov equivalence into maybe a slightly more intuitive form. So what we're going to say is that for some set of interventions I, again with observational data, two DAGs G and G prime are I-Markov equivalent. If and only if, well, first, because we have observational data, they better be Markov equivalent. So this is just G and G prime have the same set, have the same skeleton and the same unshielded colliders. Okay, and then we need something to introduce what's going on with these intervention nodes. So basically what happens with those is we also need that for all interventions, IK and I, and for all pairs, so if we have a pair XI that is not an intervention target, and we have a pair XJ that is an intervention target, then they have to be oriented. This edge from Xi to Xj has to be oriented the same way in G as in G prime. I mean, if it's oriented that way at all. Okay. So this is going to use the characterization in terms of the graphs G, I, and G prime I. So first, say G and G prime are I-Markov equivalent. Then those two graphs have the same skeleton and unshielded colliders. So if these graphs have the same skeleton and the same unshielded colliders, then the subgraph where we've just forgotten about those intervention nodes, those have the same skeleton and unshielded colliders. So really the part that we have to check is this second one. Let's take an arbitrary intervention and then a pair such that Xi is an intervention target and Xj is not an intervention target. And then we have Xi to Xj and G. Well, then in Gi, we have Xi to Xj, and then Xj is an intervention target of Ik, so we have an edge from the zeta k. This forms an unshielded collider. So in particular, any graph which is Markov equivalent to GI also has to have this edge xi into xj. So this is immediately, we're kind of basically going to the level of these intervention graphs. We say that this edge is oriented that way in here, then it has to be oriented that way in there, and then we go back to the G prime without the intervention, and it has to be oriented that way. So that takes care of the forward direction, that if they are Markov equivalent, then these two conditions will hold. So conversely, if these two conditions hold, then we can show that GI and G prime I have the same skeleton and the same unshielded colliders. Well, from this first guy, and from the fact that the interventions, they have the same targets, whichever graph that we're applying them to, that is going to imply that GI and G prime I have the same skeleton. Do they have the same unshielded colliders? Well, they have the same ones in kind of the system variables, like just the xi's and xj's. And then for the other unshielded colliders, if we have some xi to xj in GI that's not involved in an unshielded collider in G, then that's going to basically say, let's say it's involved, xi to xj is involved in an unshielded collider in GI, but not just G by itself, then that means there must be some intervention such that we kind of added this intervention variable and formed a new unshielded collider. Therefore, there must be, we must have xi is not in the intervention targets, and xj is in the intervention targets. Okay, and then so we're assuming that this is true, and we're trying to prove that they have the same, that they're I-Markov equivalent. Well, now this is exactly this condition, so this has to also be in G prime I, and then it has to be the same way in G prime. So the kind of benefit of this interpretation is it is basically telling us immediately that what we get oriented are from these kind of interventions where we separate edges. So where one endpoint of the edge is intervened on and the other endpoint of the edge is not intervened on. And this is important in terms of not, kind of overstating what we get from interventions. So if we take, for example, x1 to x2, and we have an intervention just on x2, then we form this new unshielded collider. The other way to see it is that we have one of the nodes in here and one of the nodes not in this intervention. But if we were to do something like intervene on both of them, we actually aren't getting any new information. And this is basically because, think about doing a do intervention and just setting x1 to some value and x2 to some value. Then you can't tell, the exact same thing would have happened if you had set x1 to some value and x2 to some value in the graph with the edge in the opposite direction. So actually kind of adding intervention targets, adding targets to an intervention can give you less identifiability. And in the special case of single node interventions, which are probably like the most well studied, this basically boils down to saying you can orient every edge that's adjacent to the intervened variable, or I guess edges are called incident if xi is one of the endpoints. So right, so with its parents, you know, it's kind of forming a new unshielded collider. And then with its children, you can kind of think of those as being oriented by the meek rules. Because we have this variable pointing here, and then if this edge was undirected, well, if we have it in the opposite direction, then it's forming a new unshielded collider. So this is kind of a special thing to remember. It's kind of closer to what you would expect. It's like when you're doing single node interventions, you orient all of the incident edges. Those might not be all you orient because of meek rules, so you might like figure out additional edges beyond just the ones that are incident to the node that you're intervening on. Another kind of interpretation of this, or way to remember it, you know, you would kind of think, okay, I'm intervening on this, I am able to detect the things downstream of it. I would think that their distributions are going to change, like those are going to be affected by the interventions. The ones upstream of it are not going to be affected by the interventions. And you can basically see that in terms of separations in this graph. So if we have this intervention, and then we label, you know, all of the other intervention variables as, I think I did it in the notes as this, yeah, I just said C step minus this. Well, for a single node intervention, right, we have that this, any of the parents of xi, we have xj is conditionally independent of this zeta k given the rest of them. Because kind of the only paths from zeta k to xi would either be, you know, kind of up through this zeta star variable, but we're blocking all of its children, all of its other children, and then because xi is not conditioned on, this is not a deconnecting path. So this is a d-separation in the graph, and what that's going to imply is that the probability of xj, if we set all of the rest of these to 0, and this guy to 1, which is the same as the IK distribution. So this marginal probability in the ikth interventional distribution is equal to the marginal probability. And now these were all 0, and then I can just change this from 1 to 0, and that gives me the non-interventional, the observational probability distribution. So this is just a way of reading off of the graph that kind of intuition that if we intervene on xi, everything upstream of it, that distribution won't change. And if we were to think instead about one of the children, then we would expect that this, well, we know actually, right, we're not conditioning on xi, so there's a deconnecting path right here. So they're not deconnected in the graph, and under some kind of interventional form of faithfulness assumption, if they're not deconnected in this graph, then they also, the distributions should be different. So it's kind of similar to the case of faithfulness when we're talking about observational data. You need to make some interventional faithfulness assumptions to say, like, okay, at least, you know, if something is downstream of a variable I'm intervening on, then its marginal distribution actually changes. So I can detect whether or not it's downstream or upstream. Okay. I'm going to pause here and see if we have any questions. Start erasing some of what we have. No questions? Okay, so that kind of covers at a high level what we're learning from kind of adding in interventional data. And you know, it's kind of clear, especially if you think about this characterization with single node interventions, you know, I can just intervene on the set of all single nodes, like one at a time, not like one big intervention that does all of it at once. If I intervene on them all one at a time, then I would fully orient the graph, because I would learn the edges incident to every node. That is going to be what we're going to define as a verifying intervention set. And you know, the rest of the lecture is kind of be about thinking about how small we can get that. You know, this might be super excessive. Even in the case of two nodes, we saw, well, we only need to intervene on one of them in order to learn the graph. So intervening on both of them individually, that would be way too large. And it's going to depend, you know, on kind of what sizes of interventions we're considering, and stuff like that. But first, we'll come up with some criteria to say when we have actually identified all of the edges in the graph. So, as I said, definition of an intervention set that does that. So we'll have I be a set of interventions, G DAG, then a verifying intervention set. One way to write it would be that the interventional Markov equivalence class M sub I of G is of size 1. And my kind of interpretation of why we are calling this a verifying intervention set is to kind of distinguish it from this case where you're just like a scientist, experimenter dealing with this system, and you have to come up with interventions on your own such that this holds. Well, you know, you might not be able to, like a priori, you don't actually know the graph, right? So you can't do this in kind of the optimal, minimal way. A verifying intervention set is defined particularly in this definition. We see that it's with respect to a specific graph. So the way I like to think of it is like it's kind of like teacher-student thing of like somebody, you know, the teacher knows what the DAG is, and they tell you, hey, this is the DAG. And then you want to go off on your own and kind of verify that. So you want to run some interventions that would tell you, okay, if this really is the DAG, then this set of interventions suffices for me to identify it. If they lie to you, maybe you can't identify the DAG. And the kind of canonical case of this would be in a tree graph. So if we have a tree over some variables like this, same sort of thing on the other side, then a verifying intervention set is actually just the root node. That suffices to identify the graph. Do you all see why that is?
Is there any case that the verifying intervention set can be multiple?
Sorry?
Is there any case that verifying intervention set can be multiple?
Yeah. It can need multiple interventions, and it can also have interventions that are multiple nodes. So right now I'm making a claim about the tree in particular. Always the root node, the single node intervention that just targets the root node, that alone is a verifying intervention set. So we know that we get the edges incident to the node that we intervened on as single node intervention, right? And then do y'all see why we get the other edges? So once I give you x1 to x2, what other information about this graph does that tell us? If I have x1 to x2, and then say that I had these undirected edges remaining, what does the orientation here tell us? I know somebody knows it. Yeah.
That would flow from x2 to x3 and x2
Yeah.
to x4.
Yeah, exactly. And this is because what happens if I have x3 to x2 instead? In that case, I'm going to get an extra unshielded collider. So the whole tree gets oriented from just applying the first meet rule over and over and over again. So like, even if I had more edges out here, I would apply, once I get this edge, to get the one from x2 to x3 and x2 to x4. Then I apply again if I had things below x3. So it just fans out, and I get all of the orientations from this single node intervention plus all of the meet rules, or really just the first meet rule. Okay, so the tree is kind of one end of the spectrum where there's a verifying intervention set of size, like, it's of size 1 in kind of 2 ways, right? Like, technically, this verifying intervention set is a set of interventions, and then this set of interventions, this single intervention I1, I guess its target is just the variable x1 in this case, or whatever the root node is. I had these relabeled. And this is kind of why it's a verifying intervention set, because if you just give me the tree, right, I don't know what the root node is. So I can't actually like implement this in practice. I have to have like a teacher come tell me, hey, it's this. You can go verify this on your own by doing an intervention on x1. And what we're going to talk about is kind of what happens if we don't know it. We have to kind of figure that out instead. Well, with a tree, we'll show that you can actually do this in like logarithmic number based on how many interventions or how many nodes there are, kind of by this like bisection search procedure. So you keep like halving the size of the tree until you find the root node. And generally, you know, there's going to be a gap like that. That's actually going to be kind of the best that you can do is this log factor away from the size of the verifying intervention set. Let's do another example for a verifying intervention set. So on the opposite side of the spectrum from a tree would be a completely connected graph. So if I give you let's just do a 5-node graph for now. So if I give you, I say, as a teacher that the topological order, say, of this is actually x1 comes first, and then x2, and then x3, x4, x5. One of the ways, you know, there's multiple ways I could do every single node. But if you're clever and you're trying to minimize the amount of effort that you're doing, so you're trying to do as few interventions as possible, one of the things that you can come up with is that first I'll do an intervention on x2. Okay, if you've told me this is the order, then this edge has to go that way, and then these edges have to all go out. Okay, and can we get anything else by meek rules? We have some, I think it's only one potential cycle. Maybe more. We have x1, x2, x3. And it can't go back to x1. So it would have to go this way. And I guess all of the ones that involve 1. So x1 to x2 to x4, and x1 to x2 to x5. So the only edges that we have left over are the edges here. So this is like in the kind of half of the graph that came after x2. And it suffices actually to just do another single node intervention on x4. So if we do that, then we would get the edge coming in here, the edge going out there, and then this edge would be oriented again by acyclicity. And we'll see kind of in general with a clique what a verifying intervention set will be all of kind of the even numbered nodes in the topological ordering. Okay. And we'll have a nice way of kind of uniting these two cases, just generalizing to all graphs. I should say with our complete graph like this, yes, doing every kind of even numbered node is going to be a verifying intervention set, and that's going to be for just single node interventions. We can also consider ones that do interventions on kind of multiple nodes, and then we can get this, if we're looking at the size of this set I, you could expect we just have more flexibility, so we can actually get smaller, and it can be a pretty big difference. We'll see that you can go from here, it's like basically, if we have p nodes, it's basically p over 2. It's like floor p over 2. And in the setting that we're able to do interventions that contain multiple nodes, you can again get this down to log p. So to get to our characterization of verifying intervention sets, we're going to use something we went through a little bit quickly in lecture 5, which was the following statement. So we knew that if G and G prime are Markov equivalent, then there exists a set of, or a sequence, I guess, or apply them in some order, a sequence of covered edge reversals from G to G prime. And these covered edge reversals were things that kept us in the Markov equivalence class, and that was because we were only reversing these particular type of edges where we aren't changing any unshielded colliders. It's one of the ways of thinking about it. So this was an edge xi to xj, where the parents of xi and the parents of xj were essentially the same, except obviously xj has xi as a parent, right? So all we're doing now is extending this statement to the interventional setting once again. And we're going to call the analog of these in the interventional setting I-covered edges. And that's just that xi to xj is an I-covered edge. If it is a covered edge in GI. And the reason that we don't even need to think about these additional edges in GI, these zeta k to xi edges, is because they'll never be covered, because we have this zeta star that only goes to this one, but never to the system variables. So the set of I-covered edges in G is, so I guess this is in G. The set of I-covered edges in G is exactly equal to the set of covered edges in GI. And this is going to immediately tell us from this statement that if two graphs are I-Markov equivalent, then there is a set of I-covered edge reversals from G to G prime. Okay. So I-Markov equivalent if and only if there exists a sequence of I-covered edge reversals. And what does this tell us? If there are no I-covered edges for G, then it can't move anywhere. So its Markov equivalence class has to be of size 1. So that's just a corollary. No I-covered edges. In G implies that equivalence class is of size 1. Right, and this is actually if and only if the equivalence class was of size greater than 1, then there would have to be some I-covered edges so that we could get from one of the graphs in the I-Markov equivalence class to another graph in the I-Markov equivalence class. And that's basically it for the characterization of the verifying intervention set. If you want to attach a term to kind of such a set of interventions, you could call that set a separating set for the graph. Really a separating set for like the subgraph that's just over the covered edges. So that's just like a term already from graph theory. There's like nice algorithms for computing those often, or at least computing like small separating sets up to a good approximation. And this characterization is actually super recent. So you're getting some up-to-date content in this lecture. So that reference is also in the notes. But this gives us a really nice way of thinking about what we're looking for in terms of getting this verifying intervention set so that we can actually discover the graph. It says, all I need to do is come up with a set of interventions such that for every covered edge in the graph, I separate it. I have one endpoint of the covered edge that's in that set and one endpoint that's not. I have some intervention, I guess, such that that's the case. And we can already see this for our tree graph and for our clique, or our complete graph. So in the tree graph, the only covered edges are those that come out of the root node, right? Every other edge is not a covered edge because we have only a single parent, and that parent has its own parent. So just by the fact that it's a tree, the only covered edges are the ones out of the root node, and then just intervening on the root node suffices to separate all of those covered edges. In the case of a clique, it's actually interesting. The covered edges are the ones that go in the topological order. So 1 to 2 is a covered edge, 2 to 3 is a covered edge, x3 to x4, and x4 to x5. Those are covered edges. All of the remaining ones inside of here aren't covered edges. For example, x1 to x3. x3 has x2 as a parent, but x1 doesn't. So really, it's just like this outer perimeter of the complete graph. And then we see why this kind of comes about is that in order to separate each of these edges, it suffices to pick kind of every other one. And I guess the reason that we do it with the even numbered ones instead of the odd numbered ones is like in the case of an odd numbered graph, we do it with one less. The graph with the odd number of vertices. Okay. So now we'll get to actually coming up with like nice policies, nice intervention policies that find us these verifying intervention sets. And we're going to start off by considering policies that are non-adaptive. So these are policies I kind of like to imagine in the context of like a scientific experiment. Say that you're trying to learn a gene regulatory network or something, and your interventions are gene knockouts. What you might use a non-adaptive experiment for is if you have like a bunch of students that are going to run their experiments in parallel. So you're like, okay, I know that I'm going to do like 10 interventions. I have 10 students. I'm going to go off and have them all do it on Tuesday or whatever. So I can't use the data from one of my interventions to figure out like what the rest of the interventions are. And that's the contrast, with the adaptive setting, where maybe I'm only having one student do the experiment. They're doing it Tuesday, Wednesday, Thursday, Friday, then the next week, and they're able to, come back to me and report the data from their experiment before I say what the next experiment to run is. Okay, so in the non-adaptive setting, I guess I'll just define that for you. Note that right now, as we've kind of done throughout this whole class, we've really been considering the noiseless setting. So this is the setting where a single node intervention, say, tells you all of the orientations of edges incident to it. People also think about this in kind of the finite sample setting where you don't get like that certain of information from an intervention. You might think of keeping a Bayesian like posterior over your belief of what the true graph is. Then you get new data and you update that. This is kind of the extreme case where all of your updates like collapse your belief to like a smaller and smaller set. So I'm just going to emphasize that by putting here a noiseless non-adaptive intervention policy. We'll denote it pi, and it's going to be a map from some essential graph. So I guess we can take any essential graph or I essential graph as input, and it gives a set of interventions. And then another thing that we might want to distinguish when we're talking about policies, I've already alluded to this multiple times, is that we might care about what kind of restrictions we're placing on our set of interventions. So we can also introduce this capital pi k, which is the set of intervention policies with every intervention in that policy, so all the number of intervention targets are bounded by k. And typical ones to consider are just single node interventions. Typically in like gene knockout libraries, these are what you have. They design them so that they knock out a single gene. There's some peculiarities of the technology where sometimes basically you don't control what viruses the different cells uptake, and those kind of are what's causing the genes to be knocked out. So sometimes they'll get multiple, but already if you're thinking of like 20,000 genes, you're going to at most be getting like 2 or 3 knockouts per cell. I think maybe once in a while people actually specifically design it, so if like a certain virus is taken up, then there will be a knockout of 2 or 3 genes, but you're not usually going to get something like 10 or something. Even that, not just for the practical purposes of that's like a large design space, but also that can like kill the cell if you knock too many genes out. Just really limits its function. So this, this either pi 1 or like pi k for some small k are kind of common from like an application perspective. From a theory perspective, people will also consider just unbounded size, which you can just denote by pi infinity. So it doesn't matter what size of the graph is, just pi infinity will be, we allow interventions of any size. And the type of problem that we're considering right now is what I'm going to call a minimum cost identification problem. And that's where we want to pick an intervention policy. So we want to minimize over all allowed intervention policies. the cost of the intervention set that it returns to us, subject to the constraint that it's a verifying intervention set. So subject to the constraint that our interventional Markov equivalence class at the end is of size 1. And this cost here, what we usually are going to be thinking of, I guess the results I'll give you today are where we just care about the number of interventions in that set. And we don't penalize like interventions that are intervening on more nodes. It's also been studied like what if this cost, what if you like assign a cost to every node to intervene on? Maybe some nodes, some genes say are harder to intervene on than others. Then you might have this cost be like a sum over all of the interventions in this set of interventions. And then within each of those interventions, the sum over all of their targets of the cost that you assign to the nodes, and just add them up linearly. Obviously, it's easier to do the theory if you're doing it kind of just like all the costs add up. You could do something like the cost is like a convex or like submodular or like whatever like type of function, but we're not going to be talking about those. And the result for this minimum cost identification problem in the case of a complete graph is going to be finally getting to this log p result. So we're trying to solve that, and we're going to solve it in the context of unbounded interventions. So this is theorem 2. I think I put one of the things I wrote already as a theorem before in the notes. Okay, so if we have, this holds for when we have p greater than 3 nodes, then for non-adaptive, policies in pi k, ceiling log p interventions are sufficient and in the worst case also necessary. This is actually kind of nice. So the proof of the sufficiency. Sorry, I said it out loud, but we need to write it. This is for the complete graph. So what we're going to do is basically number the vertices from 0 to p minus 1. So say that we have 0, 1, 2, 3, 4, 5, 6, 7. And then we convert these all to a binary representation. So we have 0, 0, 0, that's 0, 0, 0, 1, 0, 1, 0, and so on. And then this binary representation we're going to use to determine our intervention targets. So in particular, we're going to let the intervention I1 be the set of nodes such that that binary representation, so I'm calling this in the notes B of M. This is M such that B of M at the first position, and this is just rightmost, you can do it either way. This is just the way I wrote it out, so B of M sub 1 equals 1. So the first intervention, zeta 1, is going to target 1, 3, 5, and 7. And then the second intervention is going to target 2, 3, 6, and 7. And finally, the third intervention is going to target all of these over here with the highest values. And then the reason that this is going to form a separating set for the covered edges is because every integer will differ in at least one position in the binary representation. And that will be exactly the intervention which includes one but not the other. So say for instance we're thinking about like an edge between 2 and 5, then this is 0, 1, 2, and then 3, 4, 5. So this and this, oh look, they actually differ at every single one. So that shows that using this intervention policy, we can get away with, that's why we're getting the ceiling of log p, log base 2 p interventions. And then you can show that it's necessary. I'll let you check the base case for p equals 3, but it's basically an inductive argument of, assume that it takes, for q less than p, that it takes log base 2 of q interventions to orient. So if I pick an intervention on k nodes, then the worst case, right, is that basically the k nodes that I picked to intervene on are kind of all upstream, or like, I think it works with either upstream or downstream. But basically, they're all together in the graph, so I'm not getting any of the edges. So I still have a complete graph over those, and then I still have a complete graph over these. The only edges that get oriented are the ones that kind of cross between these two clusters. And then at least one of those clusters is going to be of size at least p over 2. And then I spent one intervention to get there. So then the log 2 p over 2 just comes out, and this becomes ceiling of log 2p minus 1, and the 1's cancel out. Okay. And this kind of intuition of using this binary encoding is basically what extends also to general graphs. And so for the complete graph, we kind of knew the structure of it beforehand. I guess general essential graphs, you could be worried have like really arbitrary structure, nothing kind of nice to exploit. It's actually the case that they decompose quite nicely. So I don't want to take us too much over 230. Maybe I'll go to like 240. So this is going to be a little bit quick, but it's in the notes. So the idea is that for a general essential graph, few things hold. First, it takes the form of what's called a chain graph. So this is a graph kind of like, it's like a type of partially direct basic of graph. We already said this is a partially direct basic of graph. And with that, we were saying, okay, there's no cycles when we just consider the directed edges. This is even stronger. It's saying there's no cycles when we also kind of consider the undirected edges. That needs a small caveat because we know that you can have just like a cycle of only undirected edges like this. This is a perfectly fine essential graph. This is in fact the essential graph for like the complete graph on 3 nodes. So a chain graph is saying there's no partially directed cycles, which means a cycle where at least one of the edges has a direction. And like if multiple edges have a direction, they all have to kind of be in the same direction. This part's not too important, but if you have a chain graph, then what you can kind of do is decompose it into chain components, which are just the connected components when you look at only undirected edges. So I have in the notes an example. If we had 1, 2, 3, 4, 5. Let's say that this was our essential graph. You can check that it is a chain graph. And then if I'm deleting kind of the directed edges, then I get the chain components. So the chain components are 1, 2, 3, 5, 6 in a chain component by itself, and then 4 and 7 are a chain component. And those chain components are chordal graphs. This is another thing that shows up a lot in graph theory. They have a lot of nice theoretical and computational properties. What this means is that any cycle, any undirected cycle, because the chain components are just undirected graphs. So any cycle of length greater than or equal to 4 has a chord, which is like a shortcut. Right, so what this says is that if I had a cycle like this, then it has to have a chord, which is an edge between 2 non-adjacent vertices. So it would either have to have this or the other 1 to 4 in order for it to be a chordal graph. And that essentially, this is actually really easy to see because of Meek rules, is that if I did have a non-chordal graph, if I had a cycle of length greater than 4 with no chord, right, then I could just take that cycle And because it's an essential graph, I know that there's some DAG in it, such that the edge is in whichever direction, so I can just kind of arbitrarily choose the direction, and then I would get from the first meek rule this propagation of 1 goes to 2, then 2 goes to 4, 4 goes to 3, then I would get a cycle. So this is why these essential graphs have chordal chain components. And then the last fact is that the orientations within each component are kind of logically independent. So if I orient an edge here, so if I orient the edge from 1 to 2, it can't help me orient the edge between 4 and 7. And that's basically, you know, if I think of what edges this could help me orient, it kind of runs up against these directed edges that are already directed. And, you know, it can't kind of skip over this set of directed edges. So I'm just going to put logically independent and hope you recall what that means. And what this lets me do is basically break up my problem into a bunch of these subproblems of just the chain components. And then each one of those has this nice chordal graph structure. And the reason that that chordal graph structure, let's go all the way over. The reason that that chordal graph structure is nice is that we can efficiently find a coloring of chordal graphs. So a coloring is a map. So we can just call it C, and it goes from the nodes in the graph to, so we would call this a K coloring. It goes to the set of integers 1 through K, and it's such that we don't have the same color between two adjacent nodes. Okay. And then basically from here, we're using that coloring to treat the graph almost in the same way as we're treating the complete graph. So first, we do a coloring of the chordal graph. Is there a question? Okay. We do a coloring of the chordal graph. Nice fact about chordal graphs is that the smallest coloring, which is called the chromatic number, is equal to the size of the largest clique. So you can find that coloring efficiently. It's of that size. Now you go in and you color your nodes according to that coloring. And then instead of taking the set I, K is equal to the M such that the binary representation of that integer M is equal to 1, we first color the nodes and then take the binary representations of the colors. So this is basically the same as in the complete graph. In the complete graph, every node has to have a different color since they're all adjacent. So we do it like that. And the example in the notes is we would say maybe have a complete graph up here on top. So that's part of the graph. And then another guy down here on bottom, say something like this. Check that that's a chordal graph. Unfortunately, I don't have colored chalk, so I can't actually do the coloring properly. But you can have, say, this node be one color, which will denote with the square. Let me just see which colors I used. So these all have to be different colors, right? So square, circle, say diamond, triangle. And then you can make this one a square, and you can make this one a diamond, right? And then each of those colors, you know, say square is equal to 0, say 0, 0. Circle is equal to 0, 1. Diamond is equal to 1, 0. And triangle is equal to 1, 1. Then you do the same thing with assigning what the intervention targets are. So your intervention targets now have multiple colors. So like in this case, zeta 1, we just need 2 interventions, right? So zeta 1 targets the circle nodes and the triangle nodes. And then zeta 2 targets the diamond nodes and the triangle nodes. Cool. So this is basically showing that, again, in the case of unbounded interventions, we can get by, you know, we had the ceiling of log 2 of p in the case of the complete graph. Now it's going to be the ceiling log base 2 of the largest clique in the graph. And typically with these bounds, you'll see the largest clique show up. I didn't have time to go over adaptive intervention policies. I just had one in there. That was the thing that I kind of mentioned with a tree. You would do kind of a bisection search. So take a look at that. And then I want to just close with 2 remarks. So the first is that we were considering, as I said, this minimum cost identification problem. You could kind of take the dual problem to that. So this is saying, like, I have an unlimited budget. Obviously, I don't want to spend, you know, like, egregiously, like, without necessity. So I still want to do this in the minimum cost way. But what I really care about is that at the end of the day, I completely know the graph. But you could consider a case where you had a budget going in, and what you wanted to do is kind of maximize the amount of information that you learned about the graph. And it could be that your budget's high enough to completely discover it, or it could be that, you know, you're going to have some edges missing or something like that. I mean, in this case, you have to kind of figure out what your measure of information about the graph is. So I was saying number of edges. You could also say like the size of the final interventional Markov equivalence class. And then the other thing, and this pertains to both the minimum cost identification and the maximum information gain, is that you could consider targeted experimental design, where, you know, essentially maybe the information that you are trying to maximize isn't some measure of information about the complete graph. Like, it doesn't require you to completely learn the graph in order to get the maximum score. You might just care about, like, out of this set of nodes and this set of nodes, which ones are upstream of the other. One that we've considered in our work is what is the intervention that kind of most makes you like a desired distribution. So you can start playing with variations of maybe the full identification problem is really hard, but maybe the thing that I actually care about takes a lot fewer interventions. You can start talking about, you know, the gap between those. So that's all for today. Hope you enjoyed, and I will see you on Thursday for the last lecture.